In this video, we're going to talk about systems of linear equations in three variables, right? And so we've already done linear equations in one variable. We did linear equations in two variables, and now we're going to add the third equation variable into our equation, and that variable is going to be generally z. All right. So these are equations of the form ax plus bx plus cz equals d, where a, b, c, and d are all real numbers, and all of them are not equal to zero. Because if they were all equal to zero, we wouldn't have an equation with any variables. Solutions to our linear equations in three variables are the set of all ordered pairs. I just lied. I meant ordered triples that satisfy the linear equation, right? So instead of having pairs, right, because we only have two variables, now we have three variables, and so we have ordered triples. And so we're going to look at an example of, okay, well, what does a solution ordered triple look like? And then also, what does that look like graphically, like visually speaking, right? And so we're going to determine if the number or the ordered triple 2, -1, 1 is a solution to the equation, and then we're going to try to graph it, all right? So remember with equations, to determine if something is a solution to an equation, you have to plug in each piece and see that it satisfies the equation, right? So this is my x, this is my y, and this is my z. So if I plug it into this equation, right, I plug in 2 for x, -1 for y, 1 for z, and our goal is to see if that equals 7. Well, 2 plus 3 does in fact equal 7, and so that is a solution, right? So yes, it is a solution, all right? What we're going to do now is we're going to try to graph, right? And so if you don't fully get this graph here, just wanted you to get an introduction to the graph, graphing in 3 dimensions, all right? This is how I graph in 3 dimensions. Other people may graph differently, but I think your textbook and I think the calculus textbook, I think Calc 3, you do 3 dimensions or multi-dimensions. And so they graph generally like this. And so I'm going to draw a sort of a diagonal line. All right, this is going to represent my x-axis. I'm going to do a horizontal line. This is going to represent my y-axis. And I'm going to do a vertical line, which represents my z-axis. And these are the positive x, y, and z axis, right? So +1, +2, +3, +4, 5, 6. These are the positive y values. 1, 2, 3, 4, 5, 6. These are our positive z values. So when I graph with 3 axes, it's almost like I'm graphing in 3 dimensions. So on our paper, we usually have 2 dimensions, because it's a plane. And think about your x and y axis being flat and then your z axis coming out of your paper, so to speak. But we don't have that, so we kind of have to draw the visual representation this way. And then your negative value, so our negative x axis is going to be extending that way. Our negative y value axis is going to extend that way. I wish I had a good horizontal line. And our negative z value is going to extend downward, right? And so we get 3-dimensional space here. When I graph an ordered pair here, my x coordinate is 2, right? Now, it's at x equals 2. So I'm going to put a reference point here because we have to do all of these together. My y value was -1, and so a y value of -1 is from my origin going 1 unit to the left, right? And so what I like to do is I like to kind of draw a rectangular, or what it's going to look like a rhombus here, but a rectangular region that represents the coordination between, or the relationship between the x and the y, right? I'm going to draw a perfectly horizontal line and a perfectly diagonal line that's parallel to my x-axis. And this is going to be sort of a reference point of where the x and the y kind of meet, all right? Then our z coordinate was 1, a +1. And so I'm going to go up my vertical line 1 unit up from my origin. And basically, I'm going to create a 3-dimensional figure. So I'm going to go up 1 unit here, 1 unit here, and 1 unit here. And basically what this does is it creates a rectangular solid. And so notice my x-axis, x value is here. So I go 2 on the x-axis, I go -1 units on my y-axis, and I go a +1 unit on my z-axis. And so the ordered pair 2, -1, 1 is given as this or coordinate, this point right here. All right. It's almost like referencing a three-dimensional figure. So that's the graph. All right. Let's go to solving systems of linear equations in three variables. One of the things I want you to know is that, okay, when we dealt with linear equations with one variable, our solution was basically a point on a number line, right? When we had two variables, we had a line in our XY plane. Now that we have three variables, we have a plane in three-dimensional space. All right, it's a plane in three-dimensional space. And so it's the set of our ordered triples that lie on that plane. All right. And so this is a system of three equations and three variables. All right. And their solutions are ordered triples that satisfy each of those equations, right? And so before we get to the graphical representation of the 3D plane, the plane in 3D space, we can check and see if an ordered triple is a solution of a system by checking to see if I plug in the x, y, and z into each of those equations that I get a true statement. Now, let's do this for this system. We've already did this for this first one because that's the same equation that we had up here. So we do know that it is a solution to that one. But let's try for these other two equations here. So we're going to substitute 2, -1, and 1 in for x, y, and z. So I'm going to have 2 times 2 plus a -1 plus a 1. We want to see if that equals 4. So that's 4 minus 1 plus 1. That does equal 4 because those are 0, right? And so here we're going to do the same thing. So it satisfies these two equations. Let's see if it satisfies this last equation. So I'm going to plug in 2 for x, -1 for y, and 1 for z, sorry. And we want to see if that equals -10. All right, well, let's simplify. That's going to be a 6 minus 2 minus 2. That does not equal -10. That is 2 does not equal -10. So since it doesn't satisfy this equation, it is not a solution to the system. All right, so there we go. And so now what we're going to do is I'm going to get back to the graphical representation of linear equations in three variables. We may have a case like this. Now, these are planes in space are basically two-dimensional areas that span in three-dimensional space, right? And so each of these, we have three planes in this figure here. And it just so happens that since these three planes intersect each other at one point, here we're going to have one ordered triple that is a solution to this system of equations right here. And so this will be a case where we have an independent system. Because remember, independent meaning we have a consistent system because there's at least one solution. And notice all three of these planes only intersect at one point. So that's independent. This equation here has an infinite number of solutions, right? All of the solutions lie on this line here. So we have three planes, 1, 2, 3, and they intersect at this line, right? Well, that's the set of all ordered triples, and since that makes a line, there's an infinite number of them. So this system is also consistent, but since there's an infinite number of solutions, then this is considered independent. This is one of the cases where we can have an inconsistent system, right? Notice I have 1, 2, 3 planes here, and none of them are pairs of them do intersect, but all of them don't intersect at one point or at one line, right? These two intersect up here, this one and this one intersect down here, this one and this one intersect at that line there, right? And so since there's not a single point or a single line that they all intersect at, then this one it will be the inconsistent system because there's not a solution. Okay. And so what we're going to do is we're going to talk about, we're not going to graph these planes. We're actually not going to be graphing these points here, I do want you to have an introduction of how you can solve a system of linear equations in three variables. And so what we're going to do is we're going to talk about how we can do that by hand, all right? The way we do this is to reduce our system of equations in three variables to a system of two equations in two variables. And then we'll fall back on what we learned from the graphical, the addition, or the substitution method when we had a system of linear equations in two variables. All right. And so that's what we're going to do here. Let's look at an example. I have this system here, right? I have three equations, right? Equation one, equation two, and equation three. I'm just going to give them a name, right? So our goal is to get rid of one of these variables, right? And to reduce this system into a system of two equations and two variables, right? So I'm just going to choose to get rid of the variable z, all right? To get rid of the variable z, I'm going to use an addition method, but on this equation with three variables. For instance, there is a 1 in front of this z here, and there's a 2 in front of that z, or multiplied by it, right? If I wanted to do the addition method, I need to get opposite coefficients in front of my variables. And I can have, if I had a -2 here, when I added these two equations together, I could eliminate the variable z, right? So what I'm going to do is I'm going to do 2 times equation 1, and I'm going to add that to equation 2, okay? So if I multiply equation 1 by 2, everything in equation 1 by 2, actually, I'm going to multiply by a -2 because I need that to be a -2 in order to eliminate that variable when I add them together. So I'll get a -8x plus 4y minus 2z equals -26. My second equation, I'm going to keep exactly the same so that I see that I have my opposite coefficients in front of that variable. When I add those together, I get a -5x plus 3y equals -13, okay? What I'm going to do next is I'm going to multiply equation 1 by 3 so that if I get opposite coefficients, so that I can get opposite coefficients for equation 1 and equation 3, all right? So I'm going to do a 3 times equation 1 plus equation 3. All right, when I do that, so I'm going to get a 12x minus 6y plus 3z equals 39. And then my third equation stays the same. When I add these equations together, I'm going to get a 13x minus 3y equals 29. All right. And so now I have two equations with two variables. And so with that, all I'm going to do now is I'm going to just think about, okay, let's use some of the methods that we already learned here, right? For instance, if I add these two equations together, I'm going to get an 8x equals a 16, right? Those cancel when I add them together. Divide both sides by 2, I'm going to get divide both sides by 8, and I'm going to get x equals 2. So one of my solutions is x equals 2. So what I'm going to do now is within this same system with two equations and with two variables, I'm going to go to one of those equations and plug in 2 so that I can find out what y equals, right? So plug in 2 for x into that first equation. That's -10 plus 3y equals -13. Add 10 to both sides, divide both sides by 3. I get y equals -1. And so with x equals 2, y equals -1, now I can go back to one of my original equations, plug in the x and y that I just found into one of those equations, and I'll be able to find or solve for z. So I had 4x minus 2y plus z equals 13. I found that x was 2, y was -1. So I get 8 plus 2 plus z equals 13. 8 and 2 is 10. If I subtract that from both sides, I'm going to get z equals 3. So my solution is 2, -1, 3. We have independent equations in this system, in this consistent system. All right, let's look at another example. I know I have a lot more space than you guys. Let's look at this example and let's solve it the same way. All right, now I could do the same thing and try to get rid of the z, but this time, notice here, I have a y, which is a 1 in front of my y here, and both of these have a -1, right? So there's already opposite coefficients here. So what I'm going to do is I'm going to do equation 1 plus equation 2, if this is equation 1, 2, and 3. And then I'm going to do equation 1 plus equation 3, right? So I'm going to do -2x plus y minus 3z equals 6, and 4x minus y plus z equals 2. Let's add them together. I get a 2x minus 2z, right, equals, that's a positive 6, by the way, equals 4. All right, so I have an equation with two variables. Now I'm going to do equation 1 plus equation 3, so I'm just going to copy those down. I don't have to multiply them by anything because I already have my opposite coefficients in front of the y. And so when I add these together, that cancels, that cancels, that cancels too. And when I add things together and everything cancels, I get a 0. And here, 6 plus 1 is 7. Well, we know good and well that 0 does not equal 7. That's a contradiction. This is an inconsistent system. Okay? There is no solution. All right? And that concludes this video. I'll see you during our next video.